All right, everyone, welcome to section 4.1, which is titled Probability Distribution. So, quick little definitions before we actually get into some examples on probability distribution. So, the first one, we got three definitions up top. You can see right here. A random variable. Now, the definition is a little strange, but I think I have a couple examples which should make sense. The random variable is going to be some unknown x. These are going to be, what they mean is it's going to be the outcomes of your experiments or your trials. And it's going to represent a numerical value. So not like choosing a card from a deck, a king. That's not a numerical outcome. And it's associated with each outcome in an experiment. Okay, so for example, a random variable can be, I don't want to say, maybe like roll a die. Okay. And the outcomes, which, again, that's going to be our unknown x. So the outcomes of rolling a die would be getting 1, 2, 3, 4, 5, and 6. And on the right-hand side, you have the probability that goes with each one. And being that you're rolling a die, and each side has an equal chance of showing up, the probability of each one is 1/6. So this shouldn't be anything new or surprise. But what I've illustrated here is a probability distribution. On the left-hand side, you have your outcomes, and the right-hand side, you have your probability. So there you go. That's what a random variable is. If you wanted to roll 2 dice, is another example here. Sorry about that. If you wanted to roll 2 dice, we actually made a giant. We've done this in a previous section, but we were looking for the sum of 2 dice, and so that will be my random variable, and all the outcomes you can get from rolling 2 dice. Right, the lowest sum you can get is a 2. And then 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are all the outcomes you can get from rolling 2 dice. And then we actually made I can't remember what section this was in, but we did do that table when we were doing sample spaces. And it laid out all of the different outcomes, and there was a probability associated with each one. I mean, right now it's not a big deal. The goal of what I'm trying to show you is that you have an unknown outcome in an experiment, and then on the left-hand side, all these outcomes are all the outcomes that could be represent that random variable. So there you go. Now there are actually 2 types of variables. Get rid of that. We have what we call discrete variable or a continuous variable. And a discrete variable, definitions are a little harder to follow because some of these terms you haven't heard before. But a discrete variable is a finite or countable number of outcomes. So I have an example here of sum of 2 dice. Something that is countable is, I think we understand countable, right? 1, 2, 3, 4, 5. But when we say finite, it means that there's a limit on the outcomes that can happen in your probability experiment. So here, the outcomes, we have 6 right here. That is a finite, and you can count them. Over here, same thing. There are 11 different outcomes here. So they are finite, and they are countable. So the difference between discrete and continuous is, maybe let's say this. If I give you 2 different outcomes, this might be the best way to explain the difference between continuous and discrete. If I give you, again, discrete variable here, if I give you 2 different outcomes, does there exist an outcome in between? Is there one in between here? Okay. So with that die, and you're rolling it, right? Everyone remembers a die, right? And you got like 1. I don't actually know where each of these numbers are, but You got 1 and 3 and 6, all those. If I give you two outcomes, 1 and 2, does there exist an outcome in between? And I'm hoping we all say, of course not. There's no 1.5 on a die. So that's, again, what makes it discrete. There is no middle outcomes. But when you're talking about continuous variables, a continuous variable, all right, uncountable means that there's way too many, and uncountable actually will come back to this idea where if I give you two different outcomes, if you're uncountable in this case, there means any two outcomes, there exists another outcome in between. Like there's just no way for you to count all of the different ones. So height of college students. So for example, if I wanted to do that, the height, like let's try this out. So that's our random variable x, and let's say somebody is 72 inches, right? And then somebody is 73 inches. So you've measured two different people, and that's the outcome. And then you go and measure somebody else. Could somebody be 72.5 inches? Like, does that exist? And of course, right? You can, if you have your tape measure and you have 72 inches, they could be somewhere between 72 and 73. So they could be 72.5. You're like, all right, well, let me squeeze that person in there then, right? So let me do that. So 72.5 and then 73. And then, the next person comes along and they end up measuring 72.8. You're like, oh, okay, well, that person goes in here. And what's happening is that any two outcomes, there is a chance that somebody else, so there's some other outcome that can be wedged in between them. And that can go on forever, right? Like, there could be 72.8, and then I could have 72.88, 72.89, 72.88879, right? As long as you have a tape measure that can measure to that accuracy, this can go on forever. So that's the idea between continuous and discrete. All right, so then we just have a couple examples. I'm going to read them. I want you to pause it, try them out, write an answer down, and then we'll go over it. So just pause and read them now. Okay, let's assume you've done that. All I want to know is determine whether they are discrete or continuous. So we have X represents the number of times you do laundry this month. Now this is going to end up being discrete because if, some, like the outcomes could be 0. You do it 1 time, 2 times, 3 times. And you could go up to, however many times you want to do them. There's only so many minutes in a day, but, this can go on forever. But that's still countable, right? And we're going to assume that, like, when you start a load of laundry, you can't do, like, half. You can't do 3/4 of a laundry. I'm not talking about, like, 3/4 of a load or something like that. I mean, like, you start it, and then you only do 3/4 of the time, and then you just stop. Like, that, we don't do that, right? You start it, and you end it. So I'm going to go with discrete on that one. Then we have X represents your salary. Now, this one is usually continuous, but I put a little thing here that says nearest cent, which means that there is actually finite number of salaries. Again, when I say finite, I mean countable. I mean, you can go up to billions and billions, but the idea behind uncountable is if somebody has a salary of like 30,000, exactly 30,000, and then somebody has the next salary would be 30,001 cent. Nobody exists between here. Like, you can't have a salary between those two, and it's due to the rounding, okay, to the nearest cent. So that's what ends up making it discrete. Now, X represents the speed of a rocket. I'm not doing any rounding, and so because of the rounding, it's going to end up being continuous, because you could have a rocket be 700 miles an hour, or 701, or 700.5, 700.55 miles per hour. And this can go on forever. So that's why it's going to end up being continuous. And then x represents your weight. Well, same thing with the height. Typically, this is going to be continuous if I don't mention anything about rounding. And the rounding is due to the accuracy of like the tape measure and the scale. If a scale, the only reason that we can't have weights of like 101, 100.1 pounds and 101.11235 pounds is because of the accuracy of the scale. The variable, yeah, you could take on any weight between those two. It's just the scale won't let you. But that doesn't mean the variable. Okay. Now, if I told you to round to like the nearest pound, then yes, now it is discrete. Next, x represents the number of math classes you've taken in your life. I'm hoping that this makes sense, that it is discrete, right? You can take 1, 2, 3, 4. It's like you are counting, and that makes that discrete. So, okay. So that's the variables. For the most part, in Chapter 4, we are only going to deal with discrete variables. We're not going to deal with continuous ones. That is the rest of the semester. All right. So probability distribution. I've already shown you an example of one. It is over here. Each one of the example of two. Each one of these is a probability distribution, and so there's just some things that we need to know about them. First is that when you set up the table, each possible value of x, that means your outcome, remember outcome, on to the right has a probability. So we do need to make sure you write the probability in this table. The second thing is that the probability has to be between 0 and 1. Like you can't have a negative probability. Like the chances of you rolling a die and like getting a 5 is, negative 20%. Like that doesn't make sense. You also can't have a probability over 1. The highest you can get is 100%, right? Which means that you're guaranteed for that outcome to happen. But you can't have something go over 100%. So all probabilities between 0 and 1. You can even have 0 and 1. Those are probabilities. Like what's the probability on a 6-sided die to roll a 7? Well, 0, because there's no 7. So it's a little sneaky, a little cheap, but that probability of 0 just means that the outcome you're looking at cannot happen. And then finally, the sum of all the probabilities. So if I go over to this table again, and I add up all of these probabilities right here, you are going to equal 1. And that has to happen for a probability distribution. Because if it doesn't add up to 1, it means you're missing something, right? There's, if you add up to 100%, it means you have counted for all of the outcomes. If it's less than 1, you either made a mistake on calculating a probability, or you're missing an outcome so that you can get up to 100%. All right, so that's what, if you remember this notation right here, that means sum. So it's the sum of the probabilities. That's what that notation is. And so it equals 1. All right, so constructing the probability distribution. So this is just the setup. If you forgot how to do it, you can go back to these 4 steps. So the first thing, it's basically a frequency distribution, right? You have a left-hand side and a right-hand side, and on the left-hand side you have your outcomes. And on the right-hand side, instead of the frequency, it's the probability. Okay, so then on the right-hand side, you list all the probabilities. Here it says on the left-hand side, you list all your outcomes, right, all the way up to your last one. And then on the right-hand side, we could say like probability of x1 all the way up to the probability of xn. Then what you want to do is find the sum of the... this is calculating the probability. Sorry, I didn't actually finish reading this. This is how you actually calculate the probability, right? It's summing the frequency. So if you want the probability of x1, you find out how many times x1 shows up divided by the total sample size. So I'm just going to write sample size here. This is if you're doing like an experiment. Okay, so a little different. I wouldn't worry too much about that. I think the probabilities you'll have in like textbooks and homework and stuff are usually pretty straightforward. All right, and then just make sure that the sum adds up to 1 and that each probability is between 0 and 1. Again, no negatives, no probabilities over 100%. So I have two probability distributions. I wrote one in a horizontal table and then another one in a vertical table just to let you know that that's possible. All right. This one is mostly like the save on space when you're typing things out because right, it doesn't take up as much vertical space. This one takes up a lot of vertical space. All right, but I want to determine whether this is a possible probability distribution, meaning does it satisfy all the conditions that I've talked about? And those conditions are, do you have probabilities between 0 and 1? So is that true? Does the sum of the probabilities equal 1? And if that's the case, then you have a valid one. Technically, like, you should check to make sure all the outcomes are present, but I'm not going to try to trick you on that one. So in this first example, we have the outcomes of 5, 6, 7, and 8, whatever this, whatever this experiment is. Those are the outcomes, and each one of them has the probability associated with it. Now I think you can clearly see the probability is all of these are between 0 and 1. And same thing with these, between 0 and 1. So in both cases, we have satisfied the first condition. Okay, so I'm actually going to label this 1 and 2. And so far, check on 1, check on 1. The next thing is, does the sum add up to 1? So we're checking condition 2. So what you could do is just on your calculator, add up the probabilities. It's 1, 5. There you go. And I want you to pause it just check the sum. Make sure it works. I'm going to do that as well. I'm calculating it right now. So on my calculator, typing it, and I get 1.07, which is not 1. So this right here is invalid. It is not a good probability distribution. Typically, when you have a probability over 1, it means that you had some outcomes that were overlapping with each other. And so you remember, like, if you remember when we were doing like Venn diagram stuff, events could have overlaps. So when you add the probability, I don't want to go over to that too much, but when you add the probability, there are chances that those events have overlaps. And if you just add them, you're adding their overlap twice. And so there's a chance that you're adding things multiple times. That's usually what happens on why you get something over 100%. Now down here, when you add these, all right, pause it. Make sure you can calculate that. But that does equal 1. All right, so it satisfies condition 1, condition 2. This is a valid probability distribution. Okay, so moving on. All right, so another definition, and this is mean, standard deviation, and variance. Again, we've talked about variance a little bit. When we're dealing with actually using it, we use the standard deviation instead of the variance. But here are the formulas. What I'm going to do is I'm going to show you how to do it by hand, and then I'll show you the calculator. I mean, we have the calculator. Let's use it. Now, it's just a formula, and so I think you may have to just trust that it works. I'm sure if you're really interested, you can search on YouTube for it, and there'll be some videos on the explanation of it. But it is pretty straightforward on calculating it. So what happens is you're going to take your outcome and then multiply it by its corresponding probability, and you're going to get a new number, whatever that is. and then you're going to add them together. Now what's happening is the mean of a probability distribution is another thing to do is, or call it, is an expected value. I don't know if the book does that or your homework, but an expected value, meaning like if you were to play this game long enough and then like keep taking the average of your outcomes, because remember, that's what a mean is. If you were to continue taking the average of all your outcomes, that's what the expected value is. That's exactly what this number is it's going to tell you the average, or when I say average, I mean the mean of all your outcomes. And then the variance and standard deviation, you can see that the formulas are pretty, they're not the super complicated, but they are pretty tedious to set up the table and all that stuff. So those we may just use the calculator on. But remember, the standard deviation is about the spread. You know, how far away are your outcomes from what you expect them to be. Okay. So for example, let's say you know, you expected the outcome to be 6, and then you have an, you know, that's the mean is 6, and then you have an outcome that's like 30. Well, that might increase the spread, right? You know, 30 is pretty far from 6. So the bigger the standard deviation, the more spread out your outcomes are from the mean, and the smaller your standard deviation, the more clustered your outcomes are to the mean. So we have this was that valid probability distribution that we just looked at, and I want to calculate the mean and standard deviation. Now doing it by hand, which is a good thing to try, right, just to make sure that you can do it, you're going to set up a table. Again, this is the probability distribution, and then you set up another column. Because remember, in the formula for the mean, you are to multiply your outcome times the probability and then add them all together. So the first thing we have to do is actually calculate x times the probability. So in this case, it's 1 times 0.16, right? Which, that one's pretty easy. It's 0.16. Then this is going to be 2 times 0.22, right? And that's 0.44. This will be 3 times 0.28. That's 0.84. 4 times 0.2. That's 0.8. And 5 times 0.14 is 0.70. All right, to calculate the mean, you add those together. So 0.16 plus 0.44, 84, 8, and 7. And I'm going to, you pause to calculate with me. So I'm typing these into the calculator right now. And I get 2.94. Now, what we're saying is that if you were to do this experiment or run a bunch of trials, so run a bunch of trials, you know, and you're getting these outcomes up here every time you run the trial. If you run a bunch of trials, you know, you're finding the mean of all those outcomes, of all the outcomes, it will be 2.94. Now that is not actually an outcome in here, but remember, we talked about this when we did mean, mode, and median, is that the mean, the value that you get is usually not an actual outcome that you can get. Okay, but it's pretty close to 3. Right. So if I had to make a bet, I would bet on 3. You know, it's closest to the actual mean. Now I want to show you how to do it with the calculator. Okay. Now it's going to come back to this table right here. This is the only thing we need. So take out your calculator, have it ready, and let me actually clear my calculator because I've already put this in. Okay, so here, and apparently I get disconnected when I switch screens on my iPad. But here we go. We have the calculator up right here. So when you click on stat, it takes you to this page where I want to click on edit because I want to get my lists. And what I'm doing is I'm putting in that probability distribution. And if you actually have values, like I do right here, if you have values in your list, you can highlight the list name, in this case like L3, and then you press the clear button, and then press enter, and then it'll clear everything out. So if you have things in L1 and L2, you can clear them out. All right, so then what we do is put in all the outcomes, and the outcomes in that, you can go back a minute, but it was 1 through 5. And then on the right side was the probability, which again, you can go and check out, but you can trust that I'm putting in what I had a few minutes ago. And there you go. Now, this is very similar to calculating the mean from a frequency distribution. We did that very briefly before. So I'm going to go back to the home page, so press second quit. I like getting back to the home page, clean slate. From here, we're going to press the stat button again. The stat button is right there. Okay. And instead of going to the list, we're going to go over to calc, so calculate. And we're going to choose the one variable stats. Now, when it opens up, it's going to tell you a list. Now, the list is going to be the outcome, so type in L1. But we do need a frequency list. And the frequency list are the probabilities, the right-hand side. And so normally, this is empty, okay, when you're doing one variable stats. So what we're going to do is we want to call in the probability. So that for me was an L2. So press second 2 and it comes up L2. And then calculate. So there we go. Let's do it. There we go. 2.94. That is exactly what we got when we did it by hand. But now we're able to do it pretty quickly. Now also, you can see right here that I get the standard deviation for free. So there was that kind of complicated formula. We can skip that and get to use this. Okay. So I'm actually going to write this number down too. And yeah, let's get back to the notes. All right. Now that we're back, we've confirmed that our mean is 2.94. So now let's go and take a look at the standard deviation. Now to do the standard deviation, is the formula here? All right, the formula is actually right here, but throw the little sum symbol on there. So what we had to do was take each outcome minus the mean, square it. So like you could see I'm making these columns. So this is 1 minus 2.94, which is negative 1.94. Then I square it, and then I multiply it by its probability. So like I get the 3.7636, and I multiply it by 0.16, and I get this. Then I add them all together. So you're welcome to try to do this by hand, but we've already, yeah, there we go. It's right here. We've already done it with the one variable stats, confirmed it was 1.27. All right, now the standard deviation, talking about the spread, it means that on average, outcomes are about 1.27 away, right? Again, without some more context, like this is not a really interesting number until we maybe we play the game so you can see how it works. But yeah, on average, each outcome is about 1.27 away. Again, that number is not an outcome, so it's not too meaningful right now. All right, so that is the standard deviation. Our next, so here, by the way, in the notes, you can pause it and you can write all this stuff down. This is how you would set up this table right here using the graphing calculator. I've already shown you how to do it with the one variable stats, so there's no reason that you have to do this. This is harder to follow, but it is exactly the way that I did this, because this is only 5 outcomes, but imagine you had like 30 outcomes. I really don't want to sit here and do this manually. And to create this table, you can either do it in Excel. Excel works really well. But I try to do it with the graphing calculator, and these are the steps. Don't worry about it. I don't advise you to look through this. You are welcome to, but there you go. All right. So now on to our... here's the expected value again, and you can actually see the expected value and the mean are the same formula. And I've already now talked about expected value. It's if you were to play the game, whatever the game is, on average, this is what you would expect to get. Like this would be the expected outcome. So okay, it is the mean of the probability distribution. We've now talked about it, and we know how to calculate it because it's the mean. All right, but why would you use expected value? Well, that gives us more meaning because it's in the name. What do you expect the outcomes to be? That would be the expected outcome. When you say mean, and someone's like, oh, the mean of this game is 4, you're like, I don't really know what that means. But if you say the expected value is 4, that has more meaning. We can figure out what that all means. Okay, but here's the example, and everyone's probably done a raffle before. So at this raffle, 1,500 tickets are sold at $2 each. So you want to play the raffle, throw in $2, and you'll get a ticket. Now, there are 4 prizes available: 500, 250, 150, 75. I actually sort of want to change this around a little bit. I do want to say there are actually 5. I want to say there are 5. There's a 500, a 250, a 150, and let's say there are 2 of these. So 2 of these. So there are 5 total now. You buy a ticket. What's your expected value? In this case, the expected value is if you were to play this raffle over and over again, how much would you expect to win? If your expected value is positive, you tend to play the game because you would expect to win. Again, this is if you were to play a lot of times. You're not, if your expected value is positive, it's not like you're guaranteed to win. It's just that if you play the raffle long enough, you're going to end up, in the long run, end up with some money if your expected value is positive. All right, so what we have to do is come up with the probability distribution. So what that means is that these are the outcomes. Like when you play the raffle, what are all the different ways that this can play out? And the first thing we have to do is figure out what those outcomes are. Now, most of the time people are like, oh, okay, well, I can win $500, I can win $250, I can win $150, or I can win $75. But you have to take into account that you had to pay for the ticket. Now, this is perfect if you didn't have to pay for the ticket. But I did. I had to pay for the ticket. It was $2. So actually, if you pay $2 and you win the jackpot, the $500, you actually make $498. That's actually what you made. And that's what's going on right here, is I'm going through and subtracting $2 off. Now, sometimes people are like, oh, okay, these are, I have 5 outcomes, but, in the actual game, there's really 6 outcomes. Because you could just not win. And if you lose $2, or if you don't win, you're out $2. So you actually have an outcome of negative $2. All right, people tend to forget that one. They always think about all the ways you can win, but forgetting that you could actually lose. You can lose $2. All right, this is kind of how you would set up the Mega Millions lottery, right? It costs $2 to play, so there's a chance you just don't win and you're out $2. All right, so now what's the probability of each of these things? Well, you have a raffle of 1,500 tickets and you only bought 1. So your chances of getting the $500 is 1 out of 1,500, right? There are 1,500 tickets. One of those tickets is going to be the grand prize. And so your chances of getting that is 1 out of 1,500. So pretty unlikely. And actually, because each one of these like prizes, he's only gonna these are gonna happen. It's gonna happen one time and one time. That means there's only one lottery ticket that's going to win the 250. And so the 248 or the 250, but you win 248. That is a 1 out of 1,500 chance. This is a 1 out of 1,500 chance. Now the next one, the 75, in which case you win $73. I changed it, so now there are 2 of these tickets. So that means there are 2 raffle tickets with the $75 name on it. So we have 2 of those. Now, how about your chances of losing? Well, if there are 5 winners out of 1,500 tickets, it does mean that there's 495 losers here. So that your chances of losing is 1,495 out of 1,500. So very likely. So here's our probability distribution, and we can change these down here because of the way I modified the problem. All right. So what I set up the table here. I'm gonna adjust this for my little edit in the problem, and so here's the formula. Because remember, what you do is you take your outcome, you multiply by the probability, which I did here, 498 times the probability, and you do that for all of them. And I gotta change this one and that one, and then you add them together. We could do that in the calculator as well, where once you put it in the calculator, so you do L1, which is all of these right here. That's what you're putting in L1. And L2 are all the probabilities. So then you would do the one variable stats on it. And then you have your outcomes, which is L1, and then your frequency list would be L2. And this is not gonna actually be the number. So because of the change, I'm actually going to put this in the calculator, and I'll show you how it works. Like before, I'll turn on the calculator. There we go. We're going to press the stat button so we can get to the edit lists. And remember, we had stuff from previous examples, so I'm going to highlight it, press clear, and there you go. So the outcomes, what was it? 298. 248, 148, 73, and -2. So those were the outcomes, and then the probabilities associated with them. So on the right hand side, there was 1 out of 1,500, 1 out of 1,500. Here's keep in mind that these are written in scientific notation because of the E. This was also 1 out of 1,500. The $73, there's 2 of them. 2 out of 1,500. And then finally, you have the -2, which is 1,495 out of 1,500. All right. Next, we go back to stat. We go over to calculate, and we scroll down to, well, it's already there, the one variable stats. Don't forget, your list is going to be L1, and the frequency, where all the probabilities are, is going to be L2. Calculate that. So there we go. We have a mean of -1.3. Okay, so let's head back to the notes. All right, so what does this all mean? Well, I get it, mean. You can expect to lose on an average. Again, the numbers changed. You can expect to lose $1.30. So being that the expected value is negative, it would be statistically unwise to play the game, all right, because on average you're going to lose. And in this case, if you ever play and you actually win the $500, again, statistically it means you should not play again, because then your overall outcome is probably going to be, a couple $100, depending on how often you played. But yeah, this is if you were to play over and over again. That's what you would expect to win. Now, what's interesting about lotteries or not lottery, well, a raffle, is think about the outcome to the person running the raffle. Again, these are usually like charity raffles, and so you should expect the charity to get money out of this. So how much money did this charity, let's pretend like it's charity, how much money did they make? Well, they sold 1,500. All right, this is more of a tangent, but $1,500 or 1,500 tickets at $2, right? So they made $3,000. But then they paid out all those prizes. So what did they pay out? All right, so this is the money in, this is the money out. So they paid out 500, 250, 150, and then two of those $75, right? And so I'm typing this into the calculator right now to see how much. Let's say this was your raffle. How much would you make? So you paid out 1,050, and then you subtract that from 3,000. So like, what's their profit here? How much did this charity make? So 3,000 minus 1,050 is 1,950. So that's how much money they brought in. Again, more of a tangent, but just, real life. This is how much they made from the raffle. All right, that is the end of 4.1. Thanks for watching.